Today I'm going to be talking about theoretical yield, actual yield, percent yield, and how to do percent yield calculations. So theoretical yield is the maximum amount of product that can be produced from a given amount of reactant. Actual yield is the amount of product produced when the chemical reaction is carried out in an experiment. So think you have 100 shots on a basketball hoop. You should, in theory, make 100 out of 100 of those shots, but you actually made 80 out of 100 of those shots. So looking at percent yield is of a product is the ratio of the actual yield to the theoretical yield expressed as a percent. So here's the percent yield equation. It's percent yield equals actual yield divided by theoretical yield times 100. The times 100 makes it a percent, and you should always get a decimal when doing actual divided by theoretical. A chemical reaction rarely produces a theoretical yield, so it's very helpful to be able to know how to calculate the percent yield, because then you are able to find out how much of your product you really made in your reaction. A lot of times these relate to limiting reactant problems, but the two problems I'm going to be going through today do not. So I'm starting with problem number 91 on page 395 of your textbook in chapter 11. So question is, lead 2 oxide is obtained by roasting galena and lead 2 sulfide in the air. The unbalanced equation is PbO solid plus O2 gas goes to PbO solid plus SO2 gas. So balance the equation and determine the theoretical yield of PbO if 200 grams of PbS is heated. So first we have to balance this equation. So let me write out the balanced equation. 2 PbS solid plus 3 O2 gas will form 2 PbO solid plus 2 SO2 gas. So now that we have the balanced equation, we know the molar ratio between all the different reactants and products. So I'm starting with 200 grams of PbS. And I know that in the end, I need grams of PbO. So when I start with PbS, I need to find my molar masses. So I already found the molar masses for these two different reactants. So I know that 239.3 grams is 1 mole of PbS. And so I can cross out these grams. I also know that for every 2 moles of PbS, I make 2 moles of PbO, which is what I'm looking for. So since this is a 2 to 2, these really are just 1 to 1, so I can cancel those out. And I know that in 1 mole of PbO, I'm going to have 223.2 grams, and that's just the molar mass. So when I plug this into my calculator, I should get 186.6 grams of PbO. So this 186.6 grams should be my total theoretical yield for this reaction. So when looking at part B, it asks, what is the percent yield if 170 grams of PbO is obtained? So I know that 170.0 grams equals my actual, while 186.6 grams equals the theoretical. So what I should have gotten out of this reaction. So if you recall, the percent yield equation is actual yield divided by theoretical yield, all times of 100. So going back, I'm going to do 170.0 grams of PbO divided by 186.6 grams of PbO times 100. So since these are the same labels, I can cancel those out. So my total percent yield for this equation equals 91.1%. So this means I obtained 91.1% of the products that I did. So this is problem number 92, also on page 395. So upon heating, calcium carbonate, CaCO3, decomposes to calcium oxide, CaO, and carbon dioxide. So part A is determine the theoretical yield of CO2 if 235.0 grams of CaCO3 is heated. So remember all the first steps we did with the first practice problem and apply them to this problem. And part B is what is the percent yield of CO2 if 97.5 grams of CO2 is collected. So again, remember what we did at the first practice problem. Go back in the video if you need help with any of the equations, and then come back when you have finished both of these problems. So looking at the answers for part 2, I know that the first step is I'm going to have to write a balanced equation. So here I have the balanced equation for the decomposition of calcium carbonate. So CaCO3, with the addition of heat, decomposes into CaO and CaO2. So my next step was I was going to find the molar masses of both CO2 and CaCO3. So CO2's molar mass is 44.01 grams per mole, and CaCO3's molar mass is 100.0869 grams per mole. So I know I'm starting with 235.0 grams of CaCO3. So according to the balanced equation, all of them have a molar ratio of 1 to 1 to 1. So this makes this problem very easy. So I then calculate grams to moles, which is this step, the moles of CaCO3 over 100.0869. And then I'm going to do the molar ratio of CaCO3 to the molar ratio of CO2, which is just a 1 to 1. And then I know that my molar mass of CO2 is 44.01 grams per every 1 mole of CO2. So when I plug this into my calculator, I should get a theoretical yield of CO2 to be 103 grams. So going on to part B, I know I'm looking for my percent yield, so I first wrote out my actual amount of CO2 that I got from this reaction, which was 97.5 grams. And then I wrote the theoretical yield of CO2 that I calculated earlier up in part A, which was 103 grams. So I went back to my percent yield calculation, as I'd shown previously. So I did my percent yield is 97.5 grams of CO2 divided by 103 grams of CO2. And I'm going to do this all times 100. So these values cancel out. So my total percent yield of CO2 for this reaction is 94.7%. Remember when calculating percent yields it's always actual over theoretical, and that you always make sure you have molar masses and a balanced equation.